Hello everybody, welcome to another video. This video I'm doing as a continuation to the Galapagos introduction that some of you commented asking for the rest of the video or for following videos. That was actually the full length of that video. I spent the rest of the time answering questions that people had live but were too specific to include in the video. So this will give some practical application to that setup that I had on the first video. Let me know what you think and what else you would like me to cover, if it's Galapagos related or any other plugin, any other thing to do in Grasshopper. And be sure to leave a comment below to let me know what you think, as well as about the new display, having the rhino at the bottom right and the Grasshopper a bit bigger so you can keep track of the script a little bit better. So with that, let's get started on making some geometry that we can plug into Galapagos and actually find a solution Galapagos can get us. So here you can see I have a construct point in the corner, and then I have a series of points that I'm arraying along the x-axis. This construct point at the very center, that's single, is going to serve as the origin for my model, so I can always call back to this. And for purposes of arraying a geometry around it. And with this, I'm now actually going to create a very simple sort of a canopy slash sort of louver design. So I'll take those points and I'll start moving them along the y-axis with another series. This is something I set up in the first video. If you'd like to see that more in depth, you can find the link for it in the description below. And I'm going to introduce a number here between 0 and 100s, and I'm working in millimeters. Sort of that way, but I'm also actually going to create a series from it in this way. I'll be able to set up a series of point rows that will turn to curves and ultimately into surfaces. So as you can see, what's happening now is that only one value, even though these two series have the same amount of values, you can see 10 here and 10 here as a default for the count on both. It's actually only assigning one value of every y vector to every other point. So what I want is to actually apply all these y values to all the points, and that's what grafting would do. I have videos in which I explain grafting and flattening much more in depth, but it'll come in the future when I'll dedicate a video to explaining data trees and sort of data structures. But in this case, this is what you need to make that grid of points. But actually that grid of points, like I said, is split up into rows. So if I do an interpolated curve and I use those points as the vertices, right? Actually I shouldn't have flattened there. So that's one thing about grafting and flattening. You can also just kind of test and see if it does what you need, or if it doesn't, then you can revert back. But as you can see, I actually get all the curves as straight lines, as they're not varying vertically. If I flatten those, you'll see that it creates one continuous curve because it's flattening it all into one data list. But again, I'll go more into the depth into that on its own video. So what I need to now is to actually apply some z-values to this to move it in the upwards direction. Right? For that, we'll move again, and we'll move in the z-axis. Plug that in there. And I need to create another set of numbers so that they're all different. I'm actually going to use a range this time, just to introduce this to some of you that may not know what it is. So the difference between a series and a range is a series you kind of build from the bottom up. You define where you start, how much you're going up by every time, and how many times you're going up. But a range is a little bit different. It first asks for a domain. So we can search domain, and we can construct a mathematical domain. And our domain start would be whatever number would be the lowest number that we would be willing to apply to the curve. So let's say, again, I'm working in millimeters, so in this case it's a little bit arbitrary, but I'll go for 80 for now. And let's say my end we'll put above 100 to 120. Okay. As you can see, it's starting to create some changes here, but this is where series and range overlap, is you have steps just like you have count, right? But the thing is, steps actually adds one more value when you output. As you can see here, when I hover over range, I'm actually getting 11 values as opposed to the 10 that I'm getting for my series. And I'll open up a panel so you can see what I'm talking about. Here you go, see? So since we start our list from 0, right, we have 10 values here. That's coming from the series and 11 coming from the range. So something I do quite often, and I actually, on my other computer, have it as a pre-made component, where you can just subtract 1. If you right-click on count, right, from the series, you can extract parameter on the drop-down menu when you right-click, and that'll give you the number that's actually inputted over there. We can bring that into our subtraction and plug in for A, right-click on B, set the item to 1, and that way our result is now 9, which is what we need for our range to create 10 values. Why this is necessary in the software, I'm not sure. It's just the way the inputs work. So now that we have them all in a slant, we want to sort of scramble those values. We can do it in multiple ways, but I'll introduce simply, it's called, let me see if I go to sets, sequence, jitter. So jitter will take that list of values, and you can set a value for the jitter, but it'll basically just randomize those values. So that jitter, as you can see here, shuffling strength, 0.0 would be no shuffling, and 1.0 would be complete shuffling. So I'll type 0.5, and you can see that we can go more regular or go a little bit crazier. And seed is really just the possibility that it could have. So that is really sort of arbitrary. It's just kind of like a randomness input. Okay, so now that we have that, I'm gonna now take these curves, right, and loft them through to create a surface. And you'll actually see there's no surface created, right? That's because it's grafted. More on that in another video. I want to specify this video for the Galapagos use, and actually take my time to explain why flattening or grafting needs to happen. But in this case, I'm going to flatten so that all those curves get treated together. And you'll see that I get my loft over here on the right. Now, let's say that this is a shader designed for some sort of shading system, and or just an overhead, right? I could use a plugin such as Ladybug to see what the most efficient geometry for the shader could be, but in this case I'm actually gonna just go for something that's a little bit quicker to show. You can see my other videos on Ladybug to see how you can set up a radiation analysis and actually then use that in combination with this video. I can also make a video where I spend more time showing specifically how to do environmental optimization through Galapagos. But in this case, what I'm going to do is I'm going to panel this whole surface so that it could be fabricated. And I'm going to see which type of paneling would be best to use the least amount of materials to make it more cost effective. So I'm going to do that by using a plugin called Lunchbox. You can find the description for this plugin. You can find the URL to find this plugin on Food for Rhino in the description below, or you can search Food for Rhino for yourself. And there's many different types of panels I can do. I'm going to base this off quad panels. So U and V divisions are then what's going to dictate the amount of panels in each direction. So you can see 11, right? And that kind of makes them longwise. And this one makes them a bit shorter. So you'll see that this value on the V divisions actually changed the shape quite a bit in section. So with that, we're ready to have a number to, as I explained in the last video, where you have to sort of have a value that you're testing against so that your other inputs can kind of shift and alter to account to try and reach maximum minimum for the measured number. So in this case, I'm going to do area. And in area, I'm going to do a mass addition to take all those numbers and receive just one for the total amount of area in panels that this is going to take. We can actually take it a step further and let's say that the panels cost $2.99 per square foot, or in this case, I suppose, per square millimeter, since that's my units in Rhino. Always make sure that your Rhino units are set to the units that you assume you're working with in Grasshopper. So we'll take those results and we could multiply it. We can multiply then that total area by the price per square millimeter in this case, and we can actually test for the full price it's going to cost us. So with that, let's set up the Galapagos. So here we have our Galapagos component, also found in your parameters tab under util. You'll see it down here, Galapagos. So our fitness, right, would be this number right here. I'm going to use an actual number parameter. Oops. And there we go. And then our genome would be the values that we want to alter in order to get that to work. So, right, again with the divisions, in this case I'm not going to take into account the labor that it would cost to install so many panels or to cut them to the size, but I have to put some kind of limitation here. So the limitation for the values that the Galapagos is going to test is really dependent on the number slider that you set. So it's going to go all the way up to 100 in this case. So I'm going to set a maximum of 20. Even that seems too much, maybe perhaps 15. And I'll do the same for the U divisions. So my maximum combination is 15. What else can we test? Or we can change the shape to also see which shape would use the least amount of material. I imagine the flat shape would. So here the jitter wouldn't actually make it, oh it does make it flat. So I want to avoid 0.0. Although I can assume that the more irregular it is, the more material it's going to use. So this actually isn't such a good value to use for testing. However, seed will take that same level of jitter and give you a different output of the same level of randomness, just applying the randomness somewhere else. So this I can actually really have no limit to how many I could have. I imagine that at some point it loops. I can see that some are very similar to others. So let's say that for the shape of the canopy I'm going to go through 30 iterations with a 0.4 jitter, or the jitter in this case would be relevant. We can use a 0.8. The domain could be something also that's used, but obviously the larger your domain, the deeper the structure is going to be, so the more material it's going to use. So I'll keep the domain for the canopy pretty regular, with a difference of 50 units. And obviously elongating the structure is going to use more material, so that's in this case not really something applicable to choose. I'm looking for testing something that will cover this amount of area, that has this sort of level of randomness to the design, and has this range for verticality. So within that, I want to see all my possibilities for panel application, represented here for the numbers used in the Lunchbox component for paneling, and testing here the iteration of randomness that we can have for the shape of the canopy. So that's actually quite a lot to test, and we'll connect our genome then to those values, 15 and 15 for UNV divisions. Remember to hold shift to apply more than one value to the genome. And so there we have, for Galapagos, testing the total level of area, or the price per square millimeter, or any other unit you're working with, and the other values that were leading up to this analysis. So as I explained in the last video, I'll double click here. I'll say I want to minimize the cost. I'll put a limit of simply a minute, just to show you that it works. And I'll start the solver. So just gathering sort of a base to work with. We can actually see here how fast it's going through all the different possibilities. So actually the seed might be corrupting this algorithm, because the seed is completely random. Galapagos may not know whether to increase that number or decrease that number, because the results of that value are completely inconsistent. And we can see there that it's actually gone through all the results, and it can give me a best result, but it's not really accurate in this case. So we'll have to replace that, or simply take it away in this case. And that's why setting up the key to a proper algorithm is to really understand the math that you're trying to test. Whether it's actually sound, whether the results can actually yield the result, whether the values that you're testing for can actually yield the result that you're looking for. And so again, here I can actually test to see, well, just by keeping the same shape, I can instead just look for which paneling is going to give me the smallest number. That's, well, that number, the seed number, wasn't really helping, but I can actually see now that some of the results at the top are 2.99, which is actually the multiplier here for the price per square piece of material. So actually that means that sometimes the mass addition is yielding a 1 or a 0 or no result. So actually the UNV divisions can't be 0, because if there's 0, then there is no surface, and so it's corrupting the data. So this is where we want to set a minimum, say of at least 3 divisions for both. So actually Galapagos, in this process of actually showing you that your data isn't actually helping your algorithm, can actually help you create better algorithms, because you realize that you actually need to set limitations for the values that you can search and ultimately understand those relationships. So again, we're going through all those results. This time we're not getting any result that equals 2.99 or a multiplier. So we know that our data now, or our results now, is more accurate. We can see the best option so far is actually this one. I'm still searching. So this seems to be our best result for this structure, to use the least amount of materials. And then we can accept that Galapagos has found this result for us, and we can actually see which divisions those were. And there was actually having 5 and 5, giving us the smallest result here. So again, this is, the more information you can put into an algorithm, the more you can actually understand how the math is relating to each other and how it's creating your result. The better your algorithm will perform, the more accurate your result will be. I wouldn't go 100% off of what I just did. This is just an example of how you would sort of approach these sort of problems. Understand that you need to set up some parameters for how your geometry is going to be done, and then understand which parameters are the ones that you can cycle through to try and get your best result, and what it is that you're testing, right? That's also important. If you're doing some kind of structural test analysis or something, or you're using a plugin for that, you need to understand what kind of stress indicator is giving you on those analysis, so you can understand then which parameters need to be changed to optimize. So let me know if this video helped. I can do another more specific example of how Galapagos can work. Just let me know what it is that you're trying to apply it to, or what it is that you're interested in, and I'll do my best to cover that. Thank you guys for watching, and be sure to leave a comment.